Okay, so next we have the cause and effect diagram, and this is one that PMI especially stresses. And this Ishikawa was the Japanese author of this idea. So if they, they could say cause and effect, or they could say Ishikawa, or they could say fishbone, and it all means the same thing. And especially in a 4-part multiple choice question, when there's 3 different names for the same thing, that's the perfect time to say, what is this? Or, this is not one of the following, and give those 3 that are right, and then come up with some crazy one, which is another good reason to know your glossary. But at any rate, and again, the major spines of the fish are generally processed, physical manufacturing process. So, like measurements, materials, people, and machines. Again, they're meant for an actual physical process, but it can be applied to a product or a service or some other kind of result. So again, what you want to do is you want to keep asking why. So if you had a problem with materials, why? Well, the product was out of spec. Or here, you had a problem with the machines. Well, why? The equipment was old. And so why was the equipment old? Because there weren't funds to buy new equipment.
Okay, so you're breaking it down. It's a continuous asking of why, how, why. Okay.
And in the literature, if you were to read up on this, the basic idea is to ask why 5 times. So it's kind of like being a 2-year-old. Why? And then hopefully that will get you to the root cause. And as I've said numerous times, and I can't say it enough, PMI is all about the root cause. Okay, next we have flow charting, and I think we've talked about this previously, basically a graphical representation. And here the flow chart has nice triangles and things, so it doesn't look so old-timey flow charting. But people often revert to, or at least, I don't know, people in our generation still revert to, the boxes and the arrows and the diamonds for decisions.
I do.
And the lozenges at the end for the start and the finish and things. Because if you can look at a flow through the process, you can identify redundancy and bottlenecks. You can look at where problems occur. Say if you're looking at, if you're looking at a process and it has, there's a whole lot of trouble between point A and point B, or point C and point D. Well, is it because maybe things aren't moving along the assembly line? Maybe they're picked up and moved physically. And you know how that is. Whenever you have furniture delivered, or whenever you move to a different house, stuff just gets nicked and bunged up when you're moving from point A to point B. Same reason I don't carry my non-solid state laptop around while it's on, because, in theory, I could have a head crash because it's not solid state. So another thing that this diagram shows, and I'm not sure if this was wittingly or unwittingly, but this is the SIPOC process. So supplier, input, process, output, customer. So if you ever asked what SIPOC is, that's what it is. Supplier,
it's called
input.
SIPOC?
Huh?
What did you say it's called?
SIPOC, which is, just another one of those geeky things that you say when you try to pronounce an acronym. So it's S for supplier, I for input, P for process, O for output, and C for customer.
Oh, okay. All right. That's where that's coming from.
Yeah. So it's good to show that kind of stuff.
That is interesting.
So, and again, you can go way in depth into this, but not necessary for the test. But if you were looking for manufacturing principles, for instance, in my project management library, I have a whole lot of books. I really admire Toyota, and I love my Toyota Highlander. But now I drive a Subaru, but that's a whole nother story. My daughter drives the Highlander. But at any rate, but Toyota came up with some fantastically wonderful ideas about quality and process improvement, and really doing things right. And truly, that is why Japanese cars made in Japan are so good, because they really, they really have worked these processes and refined them and continuously improved. I mean, there is actual fact. Okay, so the next way to look at quality data is to look at a histogram with a normal distribution overlay. So, this is your typical distribution curve. And again, like when we talked about the various sigma values, this is the kind of thing that they're looking at in terms of most normalized processes follow a normal curve. So if it's skewed to one side or the other, then you've got some kind of problem going on. So, okay. And again, each height of the because the histogram is obviously the flat top line, represents, so each of these bars, represents some portion of something. So whether that's calls received or parts that came off the line that were a little bit under tolerance or a little bit over tolerance, whatever, that's basically what this looks at. And so you can try to determine if you've got a problem, because again, when you're talking about millions of attempts at things, you should have a normalized distribution, just statistically, if everything is working well. Okay, so the next one is the Pareto diagram. And when you think of Pareto, think 80-20. So if you lined up the, all of the causes of errors or all the problems, 80% of the problems are caused by 20% of the causes. So if you think about this in your life, probably 80% of the employee problems you have are, due to 20% of the employees, or 80% of your children's issues with bad friends are because of 20% of their friends. So it's, if you start looking, how those things are when you learn a new word, it's everywhere. If you start looking at the 80-20 rule, it's everywhere. So basically 80% of the problems are caused by 20% of the reasons. So this focuses you, obviously, because we've talked about the cost of conformance, if we look at what we're going to focus on, and of course, PMI wants you to focus on the biggest bang for the buck, kind of, not necessarily the low-hanging fruit, but the ones that'll get you the best returns. Obviously, holes and poor mix are the best way to address defects in this particular diagram that we're looking at. So, basically what you do is you take, you stack all of your defect areas on the bar chart, and you rank them by, the one with the most to the one with the least. And so, others could be, it could fall somewhere into here and be a little bit higher, so it's maybe it's, not at the end, but what you want to do, I mean, if others turned out to be the top one, then you don't have the right categorization of defects. But ultimately,
so it prioritizes. Okay.
Right, so you prioritize your defects based on the number of occurrences that you see, and then you can address those in a cohesive manner. So again, it helps you get to kind of the root cause of the problem, or at least the greatest cause of the problem, so that you can deal with that. Okay, another way to do this, and again, this is for more of a physical process or an easily observable process, you would have check sheets. And again, this is a tally way of collecting data. So if you've got 4 different processes and you've got 4 potential... Huh?
Oh, no, somebody sneezed. All right.
And you've got 4 potential defects, you can find out where the intersection of defects and processes are. So going back to the old, you shouldn't buy a car that rolls off the line on a Monday or a Friday, because people are either recovering from the weekend or planning for the weekend. This would help you find out where the potential problems are in your process. So you would look at the places that had the biggest, so that, the intersection of defect 1 and process 4, there's an awful lot of problems here. And if you look down the line here, there's an awful lot of defect 1. So you want to look at defect 1. You want to look at how defect 1 is affected by process 4 or vice versa. And then you want to look at the various processes and see process 4 is a pretty heavy hitter in terms of defects. So, Is that maybe the way things come into process 4 from process 3? Is that the tools aren't sharp enough or adequate enough, or maybe they're too far away? Exactly what is the problem with process 4? And how does that contribute to your total number of errors and issues? Okay, another thing that you can do is a scatter diagram. And again, you've got to pick the right two variables, but to see if they're correlated or if they have no relationship. So obviously, if they are related, you can put a line through them, and Excel is very good at that. If you plot a bunch of points, Excel is happy to find, by picking one of the functions, the line that connects them. And basically, if it's a wide scatter, if there are dots out here and there are dots out there, it's a little bit less cohesive than something like that, which is right along the line. So say if this is defects and this is time and it's getting worse, then you've got to figure out why that is, why that cause and effect is happening. So and then we have Six Sigma, and this is the sort of the lean Six Sigma, where lean is getting the waste out of the process, and then Six Sigma is the the actual physical description of the the place on the curve and where it lies. So again, this is for large volume data that you can plot, and again, taking the form of a normal distribution of a curve. So again, here's the mean, and it doesn't look like it's right on the mean, but pretend it's right on the mean. And so within 1 sigma, or 1 standard deviation, you've got basically 68% of everything that happens. So be that defects or what have you. So know that number, that 1 sigma is 68%, and then know that within 2 standard deviations, you've got 95% of what's under the curve. Okay, and then if you go to 6 sigma, way out in the tails, you have 99.99966% of all the data, which basically translates to 3.4 errors per million touches or million events, whatever that is, piece parts coming off the line. So if you just remember 3 or 4 per million, that's good for Six Sigma. But again, you don't have to go wholly into the methodology, but the more you know, the easier it is to answer questions. So here's an example of Six Sigma, and for manufacturing, where we've got 100,000 units per day. And so if you look at a random sample of these units to verify thickness, you find that if you've got more or less than 10 millimeters, it's a problem. So if you look at the thicknesses of all the tires and you plot them, you get a normal distribution under a bell curve. So again, 68% should be within 1 standard deviation of the mean, and that's nice. But if you look at, say, Six Sigma, that's on a million tires, so that would be 10 times that many tires, you'd only have 3 or 4 bad ones. And so that is potentially an aspirational standard, but if it cost a whole lot of money to do that and your tires were $2,000 a piece, no one's going to buy those tires. So it doesn't matter that you've only got 3 or 4 bad ones out of a million. So again, always in quality, you've got that dynamic tension of cost and value. So you always want to look at that. So this is a short chapter.